Okay, this is section 8.5 in Barnett's finite mathematics, random variable, probability distribution, and expected value. Learning objectives for section 8.5. The student will be able to identify what is meant by a random variable. The student will be able to create and use a probability distribution for a random variable. The student will be able to compute the expected value of a random variable. So, what is meant by a random variable? Then the idea of a probability distribution. Then the idea of expected value. Student will be able to use the expected value of a random variable in decision making. So word problems. A random variable is a function that assigns a numerical value to each simple event in a random space S. Not exactly right to call it a function, but we'll go with it. Sample space S, a set of all possible outcomes. If these numerical values are countable, it is called a discrete random variable, otherwise continuous. And you may read that it can't be discrete if values are decimals or non-integers, but that's not true. Note, so these numbers here could be values of a random variable. Note that the random variable is neither random nor a variable. It is a function, says Barnett, with a numerical value, and it is defined on a sample space, the set of all possible outcomes. Examples. A function whose range is the number of speeding tickets issued on a certain stretch of I-10. A function whose range is the number of heads which appear when 4 dimes are tossed. A function whose range is the number of passes completed in a game by a quarterback. So you might have game 1, game 2, game 3, and passes completed might be 20, 25, 27. So basically a random variable is just a variable. It's not a function. It's a variable. Okay, so not a function. Random variable it's just a variable, like X or Y, right? In the old days. These are discrete random variables, not continuous. Simple events in the sample space S could be anything: heads or tails, marbles picked out of a bag, playing cards. The point of introducing random variables is to associate the simple events with numbers with which we can calculate. We transfer the probability assigned to elements or subsets of the sample space to numbers. This is called the probability distribution of the random variable x. So you've got a random variable x, it takes on different values. Those values, x here, for a probability distribution could be, well, it could be number of speeding tickets. I don't know how many they write in a day, 5, 10, 12. Those could be the values of x, or some values of x, and then each one has a corresponding probability, 0.1, 0.2, 0.5. The probability that big X, here's your random variable, takes on a particular value, little x, is whatever, some number between 0 and 1 for a probability. That's the y value, right, in the probability distribution. So here, well, let's see. X here, we said that's a particular value. Little x is a particular value of big X. Where big X is the random variable itself. And so here's your X and here's your Y. Here's an example. A bag contains 2 black checkers and 3 red checkers. 2 checkers are drawn without replacement from this bag. And the number of red checkers is noted. So big words there, without replacement. Meaning you take out a checker and then with the remaining checkers in the bag, you make a new valuation of probability. In probability theory, without replacement becomes equivalent to saying that you have dependent events, not independent events. Of course, each one has its own probability formula. Let big X be the number of red checkers drawn from this bag. Okay, so we've got an experiment, 2 draws without replacement, and number of red checkers, that's the random variable X. Determine the probability distribution of X and complete the table. So probability distribution of X, the values that big X can take on, that's going to be 0, 1, or 2, and each one will have a corresponding probability in this experiment of drawing 2 checkers without replacement. Possible values of X, as we just said, are 0, 1, and 2. Why is that? Well, if you're going to draw 2 checkers without replacement, you could draw black checkers both times. You could draw black and then a red, or a red and then a black. So those would be the 2 ways that you could get 1 for the value of big X. Or you could get 2 red checkers. You can get a red, and then get another red the next time. Probability that the particular value turns out to be 0. That's 0 red checkers, which means both of them are black checkers. Black on the first, black on the second. Well, we get dependent events here because the probability of black changes on the second draw since we didn't replace the black that was drawn on the first draw. Now, as you can see, probability of black on the first draw is 2/5, since if you look at the bag, you can see 2 black checkers and 5 total checkers, so 2/5. Again, probability is the number of successes which in this case would be the 2, divided by the total number of possible outcomes, which is 5. And then we have to multiply, because it's an AND. If you have an AND there, it's a multiplication rule, so we're going to multiply probabilities. Probability that you draw black on draw 2, given that you drew a black on draw 1. Well, if you draw black on draw 1, then say this black one, that gets thrown out of the bag. That leaves 4 checkers remaining, 4 possible outcomes for this second probability, and only 1 success left in the bag, only 1 black checker. Well, you multiply these fractions and you get 1/10 for the probability of 0. And so that's going to go into our probability distribution. That's going to be a row, x equals 0, and the probability of x equals 1/10. And the hint here for Barnett is that completing the row for x equals 2 is going to be easier than it will be for completing the row for x equals 1. And so, okay, we'll do that. Probability, 2 red checkers. Red on the first draw, red on the second draw. So, probability of 2, which is probability red on the first draw and red on the second draw. Well, because of this and, we are going to multiply clean this up a little bit. We're going to multiply probabilities because of the and. We're using a multiplication rule. Probability red on the first times probability of red on the second, given that you drew a red on the first. So probability red on the first, well, look at the bag. 3 red checkers, 5 possible outcomes, 5 total checkers, so 3/5 is the first probability. But now, after the first draw, maybe that one's drawn and taken out of there, we have 4 checkers remaining, 2 of which are red. So probability of 2, we're going to multiply these things, and multiplying across we have 6/20 or 3/5. 3/5 is the probability 2 red checkers. Well, now probability 1 red checker. We were told that that is harder to compute. So let's see why. Probability of 1. Probability of 1. 1 red checker in the 2 draws. Well, there are two. It's more complicated because there are 2 different ways to do it. So this is probability red, then black. That would be 1 red checker. Or by the way, I said then, but it's an and, right? Red on the first draw and black on the second draw. Or black then red. Black then red. So the or, of course, means that we're talking about a sum of probabilities. Probability of the first thing plus the probability of the second thing, and then we have to think about, well, are the events mutually exclusive? Yes, they are. So it'll be a sum of simple probabilities. Well, relatively simple. Probability red on the first and black on the second is probability of red on the first times the probability of black on the second, given that you really did have red on the first. Okay, let's make this look better. And then because of the or, it'll be plus the other way to get one red. That will be black then red, probability black on the first draw times probability red on the second draw, given that you had black on the first draw. So probability red on the first draw, we can look at the bag and see again a 3/5, and probability black on the second draw, given that you had red on the first draw, is well, 2/4. And we'll simplify in the next step. Plus probability black on the first draw. So now let's change this picture. Okay, so probability black on the first draw. So now this guy's gone. But black on the first draw happens with probability 2/5. We're going to multiply that by probability red on the second draw, given that you drew a black on the first draw, which is 3/4. So we're going to simplify all that to get probability of one red checker. Now we know that because we already have 1/10 and, wait a second, my bad, that's 3/10, isn't it? Okay, so it is not 3/5. 6/20 are 3/10. Okay, 3/10 and 3/10. I was going to remark that we kind of know this has to be 6/10, because since this is a probability distribution, and the sum of the probabilities always have to add to 1. It kind of has to be 6/10 because 1/10 plus 6/10 plus 3/10 are 10/10, which is the 1. So let's verify. We noted the property 6/20 of probability distributions, that the plus sum another of all the probabilities which are in it 12/20 have to add to 1, and we said why that is. The other property the 6/10, which we kind of think about when we do the is it a probability distribution problem. That's sometimes a problem that we have in the assignment. Is it a probability distribution? Well, you have to make sure that all of the would-be probabilities are between 0 and 1, which they are. 1/10 is between 0 and 1, so are 6/10 and 3/10. So this is a legitimate probability distribution. So here's another example. X is the number of customers in line waiting for a bank teller. And here's a probability distribution, or a would-be probability distribution. Verify that this does describe a discrete random variable. Okay, well, it's not continuous. It is a random variable. All the values of X those are actual numbers of customers that can wait in a line for a bank teller. The values are all whole numbers, which by itself doesn't make it discrete. It's not necessary and sufficient to be discrete that you have all whole numbers. The sum of the probabilities is 1. Okay, so what is this? 7/100 plus 10/100 are 17/100, 35/100, 58/100, 90/100, 100/100. So 1. And all probabilities are between 0 and 1 inclusive. That's easy to see at a glance. So it satisfies the requirements for a probability distribution. Another example. Assume random variable big X is the number of heads that show when tossing 3 coins. So the sample space that we'll analyze is head, 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 tail, head, tail, head, tail, head, 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 tail, 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 head, tail, 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 head, and tail, tail, tail. And in order to, get all of those, you can make a tree diagram. The first coin could be a head or a tail, given that the first one was a head. The second one could be head or a tail, given that the first one was a tail. The second one could be head or a tail. And then given all of the 4 initial nodes, you could get head or tail, resulting in 8 nodes at the end, and those are these 8. And the number of heads, that's how we're defining big X. Number of heads could be 0 if you get a tail, tail, tail. Or it could be 1 head if you get any of these 3 outcomes. Or it could be 2 heads if you get any of these 3 outcomes. Or you could get all 3 heads. So those are all the probabilities, or all of the outputs all of the, I shouldn't say outputs, those are all of the values of the random variable big X. Now, if you perform this experiment many times and average the number of heads, what would you expect? What if we just perform the experiment 8 times? Well, on the equally likely outcomes assumption, we would expect each of these 8 outcomes to occur once, and that will inform our expectation about the probabilities. And so 0 would happen 1/8 of the time, 1 would happen 1/8 of the time, 1 would happen, the other one would happen 1/8 of the time, the other one would happen 1/8 of the time, all of them would happen 1/8 of the time. And so on average we would expect about 1.5 heads if we just ran this experiment a lot. I mean, you look at this and you kind of think, oh wow, it should be something right here in the middle, something between 1 and 2, like 1.5. Notice the outcomes of x equals 1 and x equals 2 occur 3 times each, way more than the outcomes x equals 0 and x equals 3, which occur only 1 time each. And so we could calculate the average kind of in the way that we just described, but if we put these two events into their groups of 3, then we could calculate the way we just did, except we would just say 3 times 1 and 3 times 2. This is the 0, the number of heads, times the probability of 0 heads, which is 1/8, plus number of heads 1 times the probability of just getting 1 head and 3 for 3 coins, 3/8. The outcome 2 heads, we could multiply that by 3/8, and the 3 heads outcome multiplied by its corresponding probability, 1/8. And so what we have here is an x1 p of x1 p of x1 plus the next event times its corresponding probability, the next event. There are only 4 possible events here for this experiment. That was the cat that did that. That was awesome. Yeah, the beaver, he tries to make his mark. He's just sad that Oregon State didn't make the Final Four. And then you've got your 3-head event. Okay, pen. Okay, you've got your 3-head event times the probability of getting 3 heads. I almost said expectation, which is what you see sometimes. But look at that. X1 P1 plus X2 P2 plus X3 P3 plus X4 P4. Expected value. That looks like it could be the makings of a formula. Okay. Expected value of a random variable big X is capital sigma, which stands for the sum of the products of all of the particular values of x with their corresponding probabilities, right? X1 P1 plus X2 P2 plus X3 P3 plus da 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 plus Xn Pn. How is this interpreted? Barnett says, if you perform an experiment thousands of times, record the value of the random variable every time and average the values, you should get a number close to the expected value of x. Really, the way it should be interpreted is that if you perform the experiment infinitely many times, in other words, you get a theoretical probability, not a I want to say experiential probability, empirical probability, as opposed to theoretical probability. But expected value of x in a coin flipping experiment and other such experiments, cards, dice, the whole thing, spinner, those are theoretical expected values. So he should say infinitely many times. Computing the expected value. Form the probability distribution. Multiply each of the values of big X, each of the particular values by their corresponding probabilities. Add the results. Application. A rock concert producer has scheduled an outdoor concert for Saturday, May 14th. Now, if you're that rock concert producer, is that the right word for him? If you're that person, then it makes a big difference whether or not it rains, because that'll affect attendance and sales. If it does not rain, the producer stands to make a $20,000 profit from the concert, he estimates. If it does rain, then the producer will be forced to cancel the concert and will lose $12,000. The rock star's fee, advertising costs, stadium rental, etc. The producer has learned from the National Weather Service that the probability of rain on March the 14th is 0.4. So it's probably not going to rain, but it very well could rain. Right? A probability distribution that represents the producer's profit. And the next problem we'll do after that is to find and interpret the producer's expected profit. So there are two events here. Okay, you always have to count the number of events and know how many events you're talking about. In the flip 3 coins experiment, there were 4 possible events. 0 heads, 1 head, 2 heads, or 3 heads. Here you got 2 events, rain or no rain. Okay, so one of the possibilities is that it rains on March 14th, and the other event is that it doesn't. 2 events. Let X represent the amount of money the producer will make in profit. So x can either be 20,000 if it doesn't rain, or x equals negative 12,000 if it does rain. So those are the two expectations for the events rain and no rain, respectively. We can construct the following table. Now, the probability distribution is this part of it. That's that part of it. The above is your probability distribution. Then below we've got the expectation, right? The sum of the products of the outcomes x, which are these two numbers here. Those are, I'm sorry, these two numbers are the x's, and then you've got their corresponding probabilities. These are the products in the third column, and the sum of the products is a positive 7,200. Which is the expected value. It's interpreted as a long-range, long-term average. What's going to happen in the long run? The number $7,200 means that if the producer arranged this concert many times in identical circumstances, he would be ahead by $7,200 per concert on the average. It does not mean that he will make exactly $7,200 on May 14th. In fact, we know that he won't. He will either lose $12,000 or gain